highways carry dense traffic from early in the morning right into the late evening. Huge transport trucks thunder along the roads alongside smaller passenger cars. Which of these vehicles requires a greater force to bring it to a standstill in 10 seconds? The truck or the passenger car? Which shot at the goal would be easier for the goalie to stop in 1 second? A slow-moving ball or the ball that moves at a high velocity? Hello, I'm Nelly, and in today's lesson we will answer these questions by taking a closer look at forces acting on a body. In our previous lesson, we applied Newton's third law to a number of situations. Do you still remember the law? Newton's third law states that if body A exerts a force on body B, then body B exerts a force equal in magnitude and opposite in direction on body A. This law describes the way in which bodies interact with each other and holds true whether the forces are contact or non-contact in nature. But when we want to examine and understand this overall effect of force on a body, we have to look at each of the interacting bodies separately. These are often many different forces applied to a body. We must add those forces together to work out the overall effect of all the forces acting on a particular object. For example, here is the free body diagram of the book on the table. The weight acts down with a force of 5 newtons. The normal force of the table on the book is also 5 newtons, but upwards. I can show this direction using a sign. For this example, let up be positive and down be negative. Now when I add the forces together, plus 5 newtons plus minus 5 newtons, this gives me an answer of 0 newtons. We call the sum of all the forces acting on the body or object the resultant force. Notice that neither the shape nor the motion of the book changes as a result of these forces. We say the forces acting on the book are in equilibrium. However, if the book were to fall from a height of 3 meters, there would be the same downward force of 5 newtons, which is its weight, but a smaller upward force of about half a newton due to air resistance. Do you see that there is now a resultant force of 4,5 newtons downward? This resultant force has an effect on the book. The resultant force causes the book to accelerate downward towards the floor. In this lesson, we will focus on situations where the resultant force acting on a body is 0 newtons. This will lead us to establish and apply Newton's first law of motion. We will also introduce 2 very important terms, inertia and momentum. We will then use all these ideas to solve the problems we posed at the beginning of the lesson. Which of these vehicles requires a greater force to bring it to a standstill in 10 seconds? The truck or the passenger car? Which shot at the goal would be easier for the goalie to stop in 1 second? A slow-moving ball or the ball that moves at a high velocity? So, by the end of this lesson, you should be able to state Newton's first law, explain the terms inertia and momentum, and apply your knowledge to solve problems. Let's start by looking at what Newton's first law says. A body remains at rest or moves with constant velocity in a straight line until a resultant force acts on it. Although this may seem like a simple statement, it has some significant implications. Let's look at the 2 conditions described by the law. The first condition of this law says that a body remains at rest, while the second condition states that the body moves with constant velocity in a straight line. These conditions will not change unless a resultant force acts on the body. Do you think this is true? See if you can give some examples to support your answer. We'll have a look at the examples I thought of together. Look at this cart. It is not moving. It will stay stationary until I push it. In other words, until there is a resultant force operating on it. This soccer ball is placed on the penalty spot. It is not moving. A player must kick the soccer ball to direct it towards the goalie. She must apply a resultant force to get it to move. It won't start moving by itself. So it seems that the first part of Newton's law makes sense. But what about the second condition? The law states that a body continues to move at constant velocity in a straight line until a resultant force acts on it. This may not be as obvious. Have a look at these examples. This ice skater skating on ice continues to move at constant velocity in a straight line, but this car slows down quite quickly. Can you predict in which one of these situations there is no resultant force acting on the body? Well, frictional force acts on the car, which means that there is resultant force acting on the car. That is why it slows down. But there is a very small force of friction on the ice skater. This is so small, we can ignore it. We say the force of friction here is negligible, so she carries on at almost constant velocity, moving in a straight line. As a matter of fact, if you could find a piece of ice that is long enough, the skater could continue in a straight line and at a constant velocity almost forever, provided of course that there is no other resultant force that interferes with her motion along the way. So, according to Newton's first law, when we observe a body moving with constant velocity in a straight line, we can conclude that there is no resultant force acting on it. Just to make sure you understand this, let's think about it in another way. Can you remember the effects force can have on a body? Forces can bend or stretch or squash a body. Forces can cause a body to change direction. Forces can cause a body to speed up. And forces can cause a body to slow down. Now look at this special dynamics trolley that is traveling at a constant velocity in a straight line. Is it changing direction? Is it speeding up? Is it slowing down? I hope you answered no to each of those questions. But notice, there are forces acting on the trolley, the weight and the normal force. But these forces are having no effect on the trolley. This is only possible if the forces cancel each other out and the resultant force is 0 newtons. The forces are in equilibrium. I hope you can see that Newton's first law is really true, just like Newton's third law. These laws hold true in every situation. So far in our lessons, we have focused on the forces involved when bodies interact with each other, but the bodies themselves have certain properties that influence the way in which forces act, and the effect that forces have on the objects or bodies that they act on. It is on 2 of these properties that I would like us to concentrate for the rest of the lesson. The first property I would like us to look at is the property of inertia, the property of a body that keeps it at rest or maintains its constant velocity is called its inertia. It is important that you understand that inertia is a property of the body. It is not a force. It is that property of a body which resists a change in the body's state of motion. When an object is at rest, it remains at rest because of its inertia. Although inertia is not a force, the inertia of the body resists a change in its state of motion. In this case, the body. The boulder is at rest, so a resultant force acting on the body would have to be big enough to overcome the inertia of the body before it can cause the body to move. The more massive the body is, the greater its inertia. In other words, inertia is directly proportionate to the mass of the body. As a matter of fact, the mass of a body is sometimes referred to as its inertial mass. Inertia is measured in kilograms, and it is a scalar quantity. This means that we do not need to specify its direction when we describe it. When a resultant force overcomes the inertia of a body and sets that body in motion, the body acquires another property. This property of a body in motion is called momentum, and it is in exploring this property of momentum that we will find the answers to the questions that we asked at the beginning of this lesson. Momentum is defined as the product of the mass and velocity of a body. We can write a formula to calculate momentum. P equals m times v. The symbol, lowercase p, represents momentum, m represents mass, and v, the velocity. Because velocity is a vector quantity with a certain magnitude and direction, momentum is also a vector quantity. This means we have to specify both its magnitude and its direction when we describe it. Now, using the formula we've just looked at, let's calculate the momentum of an average truck moving along the highway. This truck and its load have a mass of 3,000 kilograms. It travels forwards with a velocity of 30 meters per second. Its momentum is calculated as the product of its mass and its velocity. So we multiply 3,000 kilograms and 30 meters per second. This equates to a momentum of 90,000 kilogram meters per second for this truck. The SI units of momentum are a combination of its base units. Mass is expressed in kilograms and velocity in meters per second. So momentum has the derived SI units of kilogram meters per second. Let's check that we have completed our calculation successfully. The truck has a momentum of 90,000 kilogram meters per second. This tells us about the magnitude of its momentum. In what direction is it traveling? It goes forwards on the highway. We can give the forward direction a positive sign. So the momentum of the truck is plus 90,000 kilogram meters per second. We must interpret this sign and write out the direction with the answer 90,000 kilogram meters per second forwards. A smaller passenger car traveling at the same velocity along the highway may have a mass of 1,000 kilograms. Its momentum is calculated as 1,000 kilogram times 30 meters per second, which gives us the momentum of the small passenger car as plus 30,000 kilogram meters per second, which tells the direction of the momentum is forwards. The final answer is 30,000 kilogram meters per second forwards. Earlier we asked the question, which one of these vehicles requires a greater force to stop it in 10 seconds? Let's investigate the situation in the lab by using a model of the situation.
Hi guys, this little vehicle running down the track has a mass of 250 grams. Now we can use this to represent the passenger car. Now this one here has extra mass on it, making its total mass equal to 750 grams. Now it represents the truck, and it means it has a mass 3 times greater than the smaller vehicle. Now what we're going to do now, we're going to let each vehicle crash into the stationary barrier, and when it does that, we're going to measure the force of impact using the force sensing device. Now both cars crash into the force sensor with the same velocity, and the force sensor measures the force of impact. Now this is the force required to stop a vehicle in a very short time. The results show that the more massive car, that is the one that is representing the truck, requires 3 times as much force to stop it than the smaller car does. So it seems that the greater the mass of the vehicle, the greater the momentum, and the greater the force required to bring it to a stop.
Thanks, Aaron. That really gives us a good answer for our question. In our example, the truck with its greater mass will have a greater momentum than the passenger car, and so it requires a greater force to bring it to a standstill. Trucks are designed to cope with this fact. They have sophisticated braking systems which apply much greater force than the brakes of a small passenger car have to handle. Trucks make use of a power-assisted braking mechanism and hydraulic air brakes to bring these massive vehicles to a standstill. The other question which we wanted to investigate is, will it take more force to stop the faster-moving soccer ball or the slower one? What do you think? Do you think that there will be a similar relationship between velocity and momentum as there is between mass and momentum? Well, I would like you to think about this as your task for today. In this demonstration, we have a slow-moving ball rolling towards a thin piece of cardboard. The ball comes to a stop when it hits the cardboard. Now we have a faster-moving ball rolling towards the same piece of cardboard. It doesn't stop as it hits the board. If we repeat the experiment with a thicker piece of cardboard, the faster-moving ball does stop. Analyze this experiment. Write a report on the conclusions you can make about the relationship between momentum and velocity from the results of the experiment. We will look at the answer to this task at the beginning of our next lesson. Be sure to join me then.